Now, welcome back to Alternating Current Lesson 3. The theory will study about the decay of current in a circuit containing an inductor L and R. Let me revise the previous one. In the previous lesson, that was alternating current 3, I explained you this diagram. When this S was switched on, the current in the circuit was not reaching its maximum value immediately. It was taking some time, and because this was due to current in this was behaving as a magnet. The flux linked to it was changing because it was opposing the growth of the current. It was taking some time. The final expression that we derived in the previous lesson was this, where I is the current at time t, where I naught is the maximum current, 1 minus e to the power minus r by l into t. And if you put t is equal to L by r, which is called the time constant, if you put t is equal to L by r, then your I had come out to be 0.632 times I naught. Means whatever is the value of L in Henry, value of R in ohm is given, and you divide that value, L value divided by R value, whatever value, if you allow the circuit to work for that many seconds, your current becomes 63.2% of the maximum current. That was the growth of current, right? So now let me come back to the present one, that is the decay of current. Alternating current, lesson 3, decay of current. So in the previous lesson we learned when this was switched on and this is not there, the current in this circuit was growing. And it was not attaining the maximum value immediately. It was taking some time, right? Now the reverse process, the switching off, means disconnecting this and how the current decreases to 0 and what time it takes to be 0. So now look at the diagram. Now when S1 is closed and S2 is open, when S1 is closed, S2 open is same as the growth of current in the circuit. If S1 is closed, this is open, means this was the circuit, and this I had explained in the previous lesson. And the equation was this in the previous lesson, alternating current 2. Now in this lesson, alternating current 3, now S2 is closed just before S1 is open. In this lesson, this is closed and this is open. This is open means it has already been, when this was closed, this was open, the current grew, and it took some time to be maximum. Now this is open, this is closed. Means this is not there in the circuit. This is not there in the circuit. This is open. This is open means this part is not complete. So this is not there in the circuit. So now the current in this circuit, because this is closed, S2 is closed, the current in this part will reduce to 0 from its maximum value I naught. And let us analyze that. So when this is closed and this is open, S1 is open, this is no more there. So this was your equation in alternating current 3. Now the EMF source E is not there, so you have to put 0 for it. Now S2 is closed just before S1 is open, therefore E is 0. The EMF of the battery is no more there. So from this equation 1, by putting E is equal to 0 here, it becomes this minus L di by dt comes to this side, it becomes positive. So this becomes minus IR. by putting e is equal to 0 in this equation. Now then rearrange it. Let's bring this I to this side and keep it below di. So it becomes di by I. How the current is changing with respect to instantaneous current I. Now bring this this L dt to this side. L is multiplied, so it comes to this side is divided, minus sign remains. Dt was the denominator, it comes to the numerator. So now this is the equation. Now let us integrate both sides. Integration of di by integration minus r by L dt. Now since this comes under the integration formula, it becomes log I with respect to base e. R by L minus R by L is a constant taken out, so we are left with integration of dt. So the integration of dt is t plus some constant of integration k. Now how to find this value k? Now here is the important thing. When this was closed, this was open, the current grew to its maximum value I naught, right? The current grew to its maximum value I naught. Now this is open, this is closed. Means from I naught it will come to 0. Now our starting time is equal to t is equal to 0. At t is equal to 0, now the current is I naught. That is what is important. That is what is important to understand. So how to find this k? So how to find this k? That is what is important. Now look, now at t is equal to 0, the current is maximum I naught. So here in this equation, put t is equal to 0, so this part becomes 0 and your I is maximum. So log I naught with respect to base e, this part becomes 0, so is equal to your k. So your k becomes log I naught with respect to b as your k. Now put this value of k, that is this thing, in this equation. In this equation, put the value of k, the integration constant. So it becomes log I with respect to base e minus r over L into t log I naught. And now it's pretty simple. Now bring this to the left hand side, it becomes minus. I am left with minus r by L into t. So then this is log I minus log I naught. Using the fundamental principles of logarithm is log I over I naught with respect to base e minus r over L into t. So what is the meaning? Therefore e raised to the power minus r by L into t will be I over I naught. So e minus r by L over t is equal to I over I naught. Now cross multiply this, we get I is equal to I naught e to the power minus r by L into t. This is the current after time t. Now this time is started from where? When it was complete, when the current was maximum and it was S2 was this is closed, this is open, this is not there. Now the time begins at t is equal to 0. Prior to that, when this was closed, this was open, the current here had become maximum. Now in this case, this is closed, this is open. Now the timing starts new timing. You have a stopwatch, you start again timing. So at t is equal to 0, now the current is equal to maximum, that is equal to I naught. So this is that time. So where tau L by R is called time constant. Why it is called time constant? If you put the dimension of L and R, this will be the dimension of time, that is second. Now let t is equal to L by R. Means you allow the circuit to work for this much time. So if you put t here, L by R, L cancels, R cancels, so I am left with e to the power minus 1. So I have put t is equal to L by R, L cancels, R cancels. So your I is equal to I naught e to the power minus 1. E to the power minus 1 is 1 by e. E has a standard value, that is 2.718. So that is equal to 1 by 2.718, 1 over 2.718 into I naught. When you divide 1 divided by this with a calculator, you get 0.368. That is 36.8% of I naught is your I after this much of time. This much of time means the current from its maximum value I naught to reduce to 36.8% of its maximum value, it requires this much time. It requires this much time. That is called the time constant. So in time t is equal to L by R, the current drops from maximum value I naught to 36% of its maximum value. That is the, so now only few lines left. So now the question is, when I will become 0? So in that expression, let us put I is equal to 0. This was our expression for the decay of current. For the decay of current means when the current had reached the maximum value, as I explained you lesson 2, when this was switched on, this was switched off, the current reached the maximum value I naught. Then after that, this is switched on, this is switched off, time is again started from 0. So the current from maximum value I naught will start reducing, and we just derived it becomes 36.8% of its maximum value after this much of time. That was your decay. So it is decreasing. So in what time it will become 0? So in what time it will become 0? So in this expression, let us put I is equal to 0 and find out the time. Because this is the current in time t. If this is 0, then what is the value of this t? Let us find out. So that is what I have asked here. When I will be 0, let I is equal to 0. So put it here, I is equal to 0. So I naught it, this was your tau was equal to your L by R. So you can write this as minus t, minus t over tau. Tau is equal to L by R. If you put L by R, R comes to the numerator, so it is in the numerator. So this can be rewritten as minus t by tau, where tau is equal to L by R. Tau is equal to L over R. Since tau is equal to L over R. Now, so I is equal to 0. We have to find out the time. Is equal to I naught e to the power minus t by tau. Now look, this is a product of two things. I naught into this e to the power minus t by tau. I naught is not 0. Then how the product is 0? Therefore, e to the power minus t by tau. Therefore, this has to be 0. That is what I have written. Therefore, e to the power minus t by tau is 0. Now, when it will be 0? When this becomes infinite, when t becomes infinite, then only this term will be 0. So, it will take infinite time for the current to be 0. Now, what is the meaning of this tau L by R, which is called time constant? If it is small, if this value in a circuit is small, the growth or decay, they become faster. Means the growth of current to reach the maximum value I naught will take place quickly, and to reduce the current from I naught to 0 will be quickly. It will take place faster. And what if the value is large? If the value of L by is large, meaning the growth and decay will be slow. Means it will take more time to reach the maximum value. It will take more time to reach the minimum value. That is why in this diagram, let me explain you in this diagram. This line, the decay of current, is not touching this axis. This goes up to infinite to become 0. And what is this? From here to here is some time. Let that time is equal to L by R. And in time L by R, the current had reduced from I naught to 30.37% of I naught. ठीक है. So if from here to here is 100%, half of it will be 50%, and 0.37 will be below this. So at time t is equal to L by R, the current from I naught, it becomes 0.37 I naught. This point is from here to here is 0.37 I naught.